Okay, as you all know, I posted the practice tests. Does anyone have any specific questions? Is anyone who's not done the practice test yet? Anyone? That's that's fine. I'm just not gonna say, oh, I'm gonna write down whoever.
Pick points. Shit.
Okay, so make sure, I wish if you haven't done the practice test yet, definitely do it tonight. In case you've got some questions for tomorrow before the test. Okay? All right. All right, so let's go through this here. Describe a solution. Solution is two parts, a solvent and a solute. There can be more than one solute, but only period one solvent. No exceptions. Something that has more than two solutes, there's a number of those. For example, air is a nice example. Air's got like 5 solutes in it. The solvent in air is nitrogen gas because it's the most. Then comes oxygen, carbon dioxide, carbon monoxide, ozone. There's a lot of little trace gases in there, but they're there.
Do you have to write that all down? Or there.
No, just say air. You can write them all down and I'll give you a smiley face.
Right.
Ah, I'm having trouble printing the thing. I was going to go through the official channels and go through the print shop. And I go to log in. You're not logged in. You're not a they put it. You're not a member of this domain. Is the official IT way of saying can't log you in. So I go and do the new user into the print shop error. They still don't recognize me. Then they ask for this number that I've never heard of. Probably an account number. As opposed to me going over to the copier right over here around the corner and print off all I want. So why in the world would I go through all that? So anyway, your test has been done for a while. I'm having trouble printing it. So it will be done though by Wednesday for sure. Okay, what's the difference between an acid and a base? Okay, where I was going with this is what's disassociating from an acid and what's disassociating from a base. So the acid is going to be and remember, there are many definitions of acids. In your next class, probably they're going to talk about at least 3 definitions. Sometimes they'll say proton donor, other times they'll, anyway, that's, bless you. There's a lot of different definitions. This is the most common one, though. This is the one you'll run into most of the time when they talk about acids. It disassociates an H plus ion. A base disassociates an OH minus. Now the 2 marks means ditto. I got a lot of questions about people who don't know what this means here. Instead of writing out disassociates, just put,
Okay.
yeah, look up. Yeah, that's another way. Think of it as an arrow up.
So,
Okay, what's an acid-base indicator? I will give extra credit for someone. What's the name of the base acid base indicator we use most of the time? Remember that big long word?
That's taking some, you
Phenolphthalein. And the P is silent. It's like pneumonia. Or
or,
what did you think it was?
I thought it was.
oh,
Well,
I thought it was. It's like a.
All right. Yeah, so phenolphthalein is the most common acid base indicator in the world. Everyone uses phenolphthalein. And the cool thing is it's very sensitive. And another cool thing about it, it produces a very, very pretty pink color. It's a cool indicator. You can remember it, yeah. On the test. That's when you need to write it down. And you'll get a smiley face along with it. So double whammy there. All right. How would you make 106 liters of 423 molar solution of propionic acid? C2H8 dry ingredient. Dry means grams from the molar mass. Okay, so let's see what the molar mass for propionic acid is. Okay, we got 3 carbons, 8 hydrogens, and 2 oxygens. Okay, the oxygens are 16 apiece. Carbons are 1201 apiece, so that's what, 3603. Hydrogens are 101 apiece, so that's 801. I mean 808. So we're looking at 11, 16. So 7611 grams per mole. Okay, so we need how many moles? How many moles of solution or of dry ingredients do we need? Okay, so that's step number 1. All right. So we're going to multiply, remember, volume times concentration equals moles. So now we can solve for how many moles of propionic acid is going to be in the solution. All right, so that's 106 liters times 423. Now we then convert that to grams. Okay, so we need 341 grams of the propionic acid. We're gonna dissolve that in 0.5 liters of water. Now, it doesn't matter if it's 0.5, 0.4, 0.6, just something less than 106. It's whatever you like, as long as it's less than what you're bringing the total volume up. And we're making one assumption here, is that if we start with 0.5 liters and we add 341 grams of acid into that, then it's not going to go over 106. That's the assumption. If that happens, what you have to do is you have to start with more water. You have to reweigh it and blah, blah, blah. Okay, but when I say, how would you make? I want directions, okay? I want directions. How do you make it? And be very specific on dry ingredients to fully dissolve it before you bring it up to final volume. Yeah,
The last part, I got the to add to 0.5 liters of H2O to dissolve, but then I can't.
then bring to 1.06 liters solution. In other words, bring it up to final volume. That make sense?
Why are we doing 0.5 and 1 when our initial was 1.6?
That's our final volume, 1.6.
Oh, I want to bring it up to final volume, right?
Yeah, but you can start with anything below 1.06. Well, you got to get it dissolved first, though.
So dissolve it in a small amount of liquid, normally water, and then you want to then bring it up to final volume.
Exactly.
So, but our final volume is 1.06, and if we were to bring that up to what you wrote down, up to final volume, it would be 1.05, not 1.06, right?
No, 1.06. Final volume.
Plus 0.5.
Huh?
1 liter plus 0.5.
No. You're gonna take and bring the volume.
Oh, I see, your 6 0. That's why I was confused.
Oh, over here, which
Yeah, I see what you did now, okay, I was a little,
this looks like this
then bring up to.
go down here.
Then bring up to 1 liter.
Yeah. You guys haven't got used to my writing yet?
We hate here.
Getting close, yes. All right, okay, remember, some of you still don't do very good setups. If you've missed the question, in other words, your answer is wrong and your setup is lousy, I can't give you partial credit. So do the setup with units and all that stuff thrown in. You gotta do that anyway to solve a problem. So if I can't follow your logic, I can't give you partial credit. And that's pretty general on all the teachers in this department. We all give, let me back up. Most of us, if not all of us, give partial credit. I don't want to speak for everyone. Some of the new teachers, I barely know their names, so I have no idea how they teach, so.
Which one don't you think that?
Show like step, is that technically a setup? So you.
Yeah, in other words, when you solve, you're fine. Yeah, because within each step, you have a little setup. It's a mini setup each time. So I can follow that fine. Now, your new teacher, however, may want you to do it all strung out like I do it in one step. It depends. Another teacher here teaches 1B. And I was just talking to her last week on her setup. She does it exactly the way I do it. Exactly. So I don't know about the two, It depends. We have 11 tenured instructors, and then there's little old me. I'm the only part-timer here. And it's funny, they're 1.0 full-time equivalents, FTEs. I'm 1.1. So I work more than them. Yet I'm part-time. It's kind of fun. All right. Describe how a crystal of sodium chloride dissolves in water. Include pictures and a description of the process. Now remember this one? So that's the crystal of sodium chloride. And because it's an ionic solid, the sodium is going to be the sodium is going to be +1, the chloride is going to be -1. So, and water, as you remember, is partially positive and partially negative. It's very, very polar. Now we're going to talk about intermolecular forces in Unit 4. And we'll talk about why water is so polar. But it's very polar. So what happens is the plus part of water attracts the negative part of the salt. So you get a attraction there. Pulls out that chloride. That's the solvating force in action. And correspondingly, we've got an attraction between the oxygen, partially negative, attracting the positive sodium ion. Now, remember, temperature means movement, unless it's at absolute zero. So that water is constantly bombarding that crystal. Each time it bombards it, it has the opportunity to pull out sodium and chloride. So the higher the temperature, the more bombardment it has. So statistically, there's a higher chance you're going to be contacting the surface and pulling out a sodium chloride set of ions. So that would be description here. Okay. You're going to describe how the positive part of the water attracts the negative chloride. The negative part of the water attracts the positive sodium ions, pulls it out. Okay, the other thing I want you to mention are the 3 forces that affect the solvating force. So temperature, physical agitation, and surface area. So those 3 affect the solvating force. When any of those go up, solvating force increases. These are directly related. Yeah.
You put them in an order, does it matter, or is like? You put like temperature and physical agitation.
Okay, temperature is more important than physical agitation. In surface area, probably physical agitation would be last, if you're going to put them in order. But that's kind of a qualitative thing. Those are the three main factors, though. You stir your sugar in your coffee to get it dissolved, as opposed to not stirring it. It'll dissolve faster if you stir it. If you heat up, put in hot water versus cold water, it'll dissolve faster. And if you use powdered sugar versus a big rock candy size of a sugar crystal, it'll dissolve faster. Every one of those are very profound effects. Anyway, so that's what I'm looking for here. And there's a lot of little parts to this. Okay, any questions about how the crystal dissolves? Now, it could be sodium chloride, it could be sugar. This is what sugar looks like. Now that's glucose. Sucrose is two of them put together. Glucose and fructose. That's sucrose. So there's a lot of OHs on here, and the OHs is what makes water polar. So if you have a lot of OHs, that means sugar is very polar also. So sugar is going to act the same as sodium chloride in a solution. Yeah.
Diagram, the OH at the very bottom. They're like little S's.
Oh, yeah. The little s's are partial. In math and in science, we use that little squid. It looks officially like this. If I drew it really big and really carefully. And that means partial. In other words, it's not fully negative or it's not fully positive. It's partial negative, partial. In other words, water is not an ion, but it's very polar though. Acts like an ion. It's not an ion. In other words, it's the next step from being an ion. Okay, now we're going to make the same thing, only this time 105 instead of 106. We're going to make the same thing from a concentrated solution rather than dry. So the important equation here is the initial moles equals final moles. When we're talking about liquids, moles is the same as volume times concentration, initial, volume times concentration, final. So the initial concentration, that's the concentrated stuff, is going to be 14.3 molar. That's moles per liter. And we don't know how much of the concentrated stuff we need to start. So we're going to leave that as a variable. And what we want to end up with is concentration 4.23 moles per liter times 105 liters. I'm going to solve for the initial volume of the concentrate. Okay, so we end up 0.311 liters of the concentrated solution. So how would you make? We need directions again. So we're going to take So we're going to take 0.311 liters of the concentrate and add water to the final volume of 105 liters. Everyone okay?
Volume. Is it volume, short volume?
Yeah, and the initial volume is concentrated, final volume is the dilute. Now we could go the opposite way. If the initial volume is the dilute, and how will we get to a more concentrated final volume? We're not adding water. We add water, it'll get more dilute. How do we take it away? Heat or, that's right, perfect. Heat or evaporation, yeah. So to take something dilute and make it more concentrated, you have to take out water, not add it. If you add it, you're diluting it. But still holds, initial moles equals final moles, regardless of whether you start with concentrated or start with dilute. Now, if we had the same problem, we could say, how do we make, let's see here, how would I do this? How would I make 1.05 liters a solution of 14 molar solution of from a 4.23 molar solution? And you have to say you evaporate off X amount of water. Now, that's not going to be on the test. I'm just saying that's how you'd approach it, though. That's why dilute acids sitting out on the counter are really dangerous if you leave them out in the open, because they evaporate, but the acid doesn't evaporate, only the water. So that acid gets more and more concentrated. So if you have a lab on Thursday, by Monday, that water has, a lot of it is evaporated. And the more concentrated it gets, the slower the evaporation process becomes. So a dilute safe acid can become a concentrated dangerous acid if left out. Okay. What's the resulting concentration if we basically mix these two solutions? All right. So concentration is going to be, so we need moles in the end, and we need liters in the end. So what's final volume? Okay, we have 434 liters and 356 liters. So we're looking at now we need to figure out the moles. Okay, so we're going to have 434 liters times 156. And I purposely write molar in moles per liter. So it's obvious the liters cancel. Let's call this solution A, solution B. We have 22.04 moles total between solution A and solution B. So now we have total moles, total volume. Now,
So at the very top, when it says like, be aware of sig figs. For solution B, would you not make that 15.3?
yeah, you have to, I always recommend rounding at the end. Yeah, so you round in the middle. Like I rounded a little bit. If you round in the middle, sometimes you have rounding errors. Now, on my test, and your answer is slightly off because of rounding errors, I will not take off anything.
Just kind of like.
But just in
look up,
general,
just round, yeah.
yeah, just use all the 29 sig figs in the calculator. And at the end,
You find that should not be.
yeah. Okay, so we have 22.04 moles final over 790 liters final. So we want moles per 1 liter, not 22 liters. So we divide by 7.9. So the final concentration of sodium chloride is going to be 2.79. Now, it's got to be intermediate. Let's see if that makes sense, that answer. Okay, we're starting off with 1.56 molar concentration and 429 molar concentration, and approximately the same volumes. So basically, what we're doing is diluting them. We're diluting the concentrated one down a little bit with the dilute one. So our answer should fall between 156 and 429. And it does. Okay, this is a titration problem. Now remember, titration is when we have moles of acid equals moles of base in an acid-base titration. So the goal here is to find the unknown concentration of acid. So we have, and it's 1-to-1 from the balanced equation of moles of base equals moles of acid. Now, I was asked by a student from my last semester, and they're in 2A, and they asked me a question on this specific. And I said, write out the balanced equation. It could be you're working with a diprotic acid or a triprotic acid, which means it's not going to be 1-to-1. It's going to be 1-to-2 or 1-to-3. So always be aware of the stoichiometry and the balanced equation. Okay. So this balanced equation is going to be and the unknown acid is going to be HCl. So that's going to be water plus sodium chloride. And it's balanced as written. That means this is 1 to 1. So if we know the moles of one, we know the moles of the other. That's the essence of titration. It's looking at what it's going to take to an acid-base titration. What is it going to take to neutralize the acid or the base at pH 7? So moles of sodium hydroxide. Look at that first. I'm going to go. Then we're going to have moles of acid. After we reach the endpoint from the indicator, when the indicator turns pink, we're at pH 7. So now we know moles of acid equals moles base. Unless it's pH 7, that's not true. That's why we have to use a pH meter, which is the slickest way, but a most expensive way versus a chemical. And your choice of indicator should be close to what the pH meter says. And phenolphthalein is very close to a pH meter. That's why we always use phenolphthalein. Okay, so we have moles at neutralization. Moles of base equals moles of acid per balanced equation. Now, if we were using oxalic acid, that's a diprotic acid, that equation would mean we'd have 2 NaOHs for 1 oxalic acid.
Doing that we're using hydrochloric acid.
Yeah.
Is it safe to assume that on the test as well?
Yeah. In other words, a simple strong acid. Usually it's hydrochloric acid. In your next class, though, they're going to throw in sulfuric acid or oxalic acid or citric acid, which is a mono, di, triprotic acid, which that means in the balanced equation, you're not going to see a 1-to-1, you're going to see a 3-to-1 or 2-to-1 or 1-to-1. That's why stoichiometry is really important. And if you guys have Stu Hayes next quarter or next semester, guaranteed, we'll see that. And Stu Hayes really likes to always refer back, like I do, always refers back to the equation, the balanced equation. That is your key. It'll determine everything. I was interviewed for a position a while back, and I was asked specifically this question. A student was having trouble in their titration, and they weren't getting the right results. It was because the student was not looking at the balanced equation. He was assuming 1-to-1, and it was oxalic acid, so it was 2-to-1. That was the question on the interview. Yeah.
So our test purposes, though, we are only worried that 1 molecule of base, 1 molecule of acid can stay under.
Probably be balanced pretty right.
So it's balanced as written. It's very simple balancing, but I'm just saying though that it's simple if they have a diprotic acid as well, but they're not all acids are not all created equal.
Yeah.
Yeah.
In that case, it would be half the number of moles of acid.
Yeah, or double the base. Yeah, same thing. Yeah. Yeah, Sierra.
Let's say if we had, if we wrote it and it was not balanced, we have to do the steps in order to get it.
Always assume it's not balanced.
That is,
Correct. But I'm just saying though,
oh,
that assume it's always not balanced.
that's the first thing you write. Okay.
Yeah. And it's a simple one because it's already balanced. It could not get any simpler. But the main thing is what's the ratio between the acid and base? 1-to-1. Okay, so to get moles of base, you need volume plus concentration, and volume needs to be in liters. So we need to convert milliliters to liters. So that's going to be 0.2567 liters. I'm gonna leave it. I'm not gonna do any rounding yet. So we're looking at we don't know the concentration of acid. So that's the setup basically. So we're going to solve for C. Okay, but this is the equation we base everything off of. Moles of base equals moles of acid.
Did you round your answer? Or did you round your initial concentration of the?
No, I didn't round it. I didn't round anything till the end.
I'm getting 0.108 5.
Think your one's supposed to be a 6 now.
As your final answer?
No, that's my initial concentration unit. When you multiply 0.423 moles by 0.02567 liters,
Okay,
I'm getting a different number than you're getting. You got 0.0200. I'm getting 0.108, which will obviously change my.
no, it's 20 milliliters of unknown acid. That's 0.0200 liters.
Right, I'm getting a different number for that.
Oh.
How are you getting?
Is your
And
multiplying?
I open.
Oh,
Yeah, almost kind of. My, I could say.
fine. This number, what is-
Right.
which then produces.
It's bundle. Bundle was.
Meters.
Yes, they said, acids,
I'm-
but, like, we get it.
You multiply these two together, they get 101, right? Or 108.
Yeah, 101.
Let's see, this is equal to O2 times the unknown acid concentration. So when you take your 108, divide by O2, you'll get that. So go ahead and do that.
About zero.
And you're getting that from the initial question where it gives you 20
Yeah.
milliliters.
Yeah.
20 milliliters is equivalent to 0.02 liters.
So divide this. By O.
With. Oh, this game show. What is it, not just sense? Yes. Supposed to be a fix.
Let's look at the. This one.
It's the,
There's supposed to be, I don't know, it's next, but I think you put one right there, that's why, the number's not right.
Oh.
I coded. It's 0.256.
so you have 0.0251.
Yeah, I think that's what it
Supposed to be 6 7.
Where did you get this number in? 25.67? Yeah. Right on 1,000, that's 0.02567.
But in the bottom.
The top one is correct, because the bottom of the, like, you put in the one and then you put back in there.
Yeah.
Well, that times that, I know that,
Yeah.
that's what you did.
Yeah, cause you have in your
The only
your
difference,
setup is 0.02517, not 6. There you see it. Supposed to be a 6, 5, 6, 7,
oh,
now 1.
are you trying to tell me what 6 and 1 is about the same?
I guess.
All right. The stock claro.
You figured out your mistake.
Entiendo.
Yeah.
Yes, this should be a 6. And I sloppily wrote my 6 to look like a 1, so this should be a 6, right? Let me see you say answer.
Respuesta. Respuesta.
La puesta.
Respuesta. Respuesta.
Es.
Esta basura.
Something. Sure.
So what, when you do it, what do you get? 5 what? That?
Yeah.
Okay. Thank you. You know, I've been trying to write more clearly so that I don't get stuff like that.
But it's hard to write like that in Japanese.
I know, but
Yeah.
I'm trying. And because, see, I made my own, I messed up my own stuff because my writing isn't clear. So how would you say that? Mi escriba no está claro.
Yeah.
All right. All right. What's the hydrogen ion concentration of pH 5? Okay. Now you're going to have a simple pH question on the test. Okay. So pH means the negative logarithm, the negative exponent. So remember in your head, logarithm exponent. So that's, and it's the negative of it. So 5, negative of 5 is negative 5. So that's 10 to the negative 5 moles per liter. And that's as tricky as we're going to get in terms of pH. Just going from pH, concentration to pH. Now, if I said, what's the pH of 0.345 molar solution? Then you take the logarithm of 0.345. So that would be no units. pH has no units. So that's it as far as pH. Concentration to pH, pH to concentration. Okay, for the following chemical reaction balance, right, balance and write both the molecular and net ionic equations. So you need your solution chart. So this is a double replacement reaction because there are no metals here. Double replacement has no metals. It's just ionic solution, ionic solution. Okay, so we're going to swap the cations. So the K goes down, the PB goes up. So our new equation is and cobalt, if you look on your common ion chart, is a -2. Potassium is +1. So how many Ks do we need? 2. Good. Okay, is it +2 or +4? Yeah,
It should be +4 because of two. Carbon.
and they're -2 apiece. So that's right. So this needs to be +4. So then we need 4 chlorines. Now, how do you know it's +4? Okay, looking over here, cobalt is -2. And we have 2 of them. That makes that -4. And against 1 lead, that means that the lead has to be a +4. So this is a 4 now. Okay, so that's the molecular equation. Looking on your chart, lead chloride is going to be black. So that means it's a solid. Looking on your chart, potassium is all white, all the way down. That means potassium carbonate is in solution, so it's AQ. So that's the molecular equation. And it's balanced. The net ionic equation. Net ionic means did something happen? Yes, we formed a solid. So we're going to take so we have lead +4 aqueous plus 4 chloride aqueous gives us lead chloride. And it's going to be plumbic chloride or lead 4 chloride. Spectator ions. Potassium, cobalt. Okay. So this involves a metal, means it's single replacement. Single replacement, we need the activity chart. And I will give you that with the test, along with the common ion chart, by the way. And I don't have the reactivity chart in front of me. Does anyone have theirs out by any chance? I have one in this pile. Now, does everyone have one of these? I don't have a reactivity chart with me. I need to borrow some. Actually, I have one electronically here. Let me just pull that up here so that. Okay. So we're looking for magnesium. What was the other one? Lead and magnesium. So the question is magnesium above lead? Okay, here's lead down here. And magnesium is above lead.
Yeah.
So when the metal is above the ion, it goes. Magnesium is +2, so we need 2 nitrates. Lead is a +2 also. Now, I may ask, why does this reaction go? And you will say, because metal magnesium is above lead on charter table. So if I say why, that's what you put down. The metal is above the ion. Oh, thought you were raising your hand. Okay, oxidation versus reduction. Oxidation is loss of electrons. Reduction means gain of electrons. Now, when you get in your next class, they're going to talk about oxidation numbers. When an oxidation number increases, it's oxidation. When the oxidation number reduces, it's called reduction. That's where the word reduction comes from, as the oxidation number is being reduced. Okay, so in an oxidation reduction reaction, oxidation gives up the electrons, the reduction receives them. Donor, recipient. You know, I think it's 1:45. This is gonna take another 15 minutes minimum. I will finish this out on a second video. So that we can get started in lab time. And Aaron, could you send me a note to remind me to do that?